Hey, YouTube. Hey, Brant.
Hello.
Hey, I'm excited to have you on the show. We're going to have a lot of fun. Before we get to the official podcast, just want to tell people listening, if you have questions or thoughts for us, please throw them in the live chat and we'll try to make them part of the show. If you're watching this afterwards, well, there's no live chat, but we still appreciate you watching the show. All right. Ready to kick this off?
Yes, I am. Thanks for having
All
me.
right. Yeah. Brant, welcome to Talk Python to me.
Thank you for having me. I'm excited to talk about some of this stuff.
I am absolutely excited about it as well. I feel there's a huge renaissance happening right now, or has been happening for a little while now, around Python performance.
hmm Yeah, no, it's exciting to see, especially in just the last couple of years. You definitely see these different focuses, whether it's improving single-threaded Python performance, multi-threaded Python performance, Python in the browser. There's a lot of really cool stuff happening right now.
Oh, absolutely. Yeah. Oh, if we could talk WebAssembly and PyScript and all that, that is a very exciting thing. There's probably some performance side around it, and I think it'll be, maybe something we could touch on, but that's not the main topic for today. We're going to talk about just the core CPython and how it works, which is going to be awesome. Some work you've done with the team there at Microsoft and your contributions there. Before we get into all that stuff, though, let's start with your story. How did you get into programming in Python?
Yeah, so I originally studied computer engineering, so like hardware stuff at UC Irvine. And around my like third or fourth year, so like 2017, I encountered Python really for the first time in like a project setting. Basically, it was a senior design project. We get to kind of make whatever we want. So we made this cool system that basically it's you point cameras at a blackjack table and it detects card counters. And if you want to do something like that in 4 months or whatever, Python is kind of the way to go.
Yeah, the CV stuff there is really good, right?
Yeah, so it was NumPy and OpenCV, and that was kind of my first exposure to this stuff. And so I learned that I like developing software a lot more than developing hardware. So I kind of never looked back and just went full in. About a year later, so like 2018, I opened my first PR to the CPython repo, and it was merged. And a year after that, 2019. Oh, there's this standard library module called Module Finder. Basically, it's one of those ones that's kind of just a historical oddity, and it's still in there. Basically, you can run it over any Python script. It detects all the imports, and so you can use it to build an import graph. And I forget exactly what I was using it for. I think it was for work. And I ran into some bugs that had been just kind of lingering there for years. And so I submitted patches for a bunch of them. And so that was kind of my first experience contributing to open source in general. That PR was actually open for a while. It was open for I think it was like a month or two or something like that. So in the meantime, I contributed other things to like MyPy and TypeShed. But that's still my first open source contribution if you count the data was open.
Does it count as the beginning or the end of the PR, right?
Yeah, exactly. Because those can be very different things sometimes.
They can be very different. We have now in CPython, we have just in Python, I guess, we have the developer in residence with Lucas Schlenga, and he's there to sort of facilitate making that a lot faster. And I feel like, people's experience there might be picking up speed and improving.
Yeah, no, I think that's a great thing. And in general, just seeing this kind of shift towards full-time Python core development, being funded by these big companies is really exciting to see. And I think it improves the end contributor experience, the user experience, and, just gets things done, which is nice. I don't have any numbers, but I imagine there are fewer of those kind of lingering, months old PRs than there were, back when I first started.
Yeah, I think
way long ago, 4 years ago.
so far back in the past.
So long. Yeah. And so that was like 2018, 2019. I became a member of the triage team, which is basically a team for people who are kind of more involved in Python than just your average drive-by contributor. So while they're not full core developers with they basically can do anything a core developer can, except vote and actually, press the merge button. So that was really nice because it made doing things like reviewing PRs easier, tagging issues, closing issues, that sort of thing. And then a year later, I became.
How do you get the experience for that? Like, how'd you? It's one thing to say, well, I've focused on this module and here's this fix, and it's another to say, give me anything from CPython and I'll assess it.
Well, it wasn't give me anything from CPython. It was, it made it part of my morning routine to, wake up, go to a coffee shop, order a coffee, and just for a half hour look at newly opened issues and
I see. Pick the ones you felt qualified.
Yeah. Yeah. Well, I focus mostly on PR review for new contributors. So basically, I had filters set up that said, show me all the PRs open the last 48 hours from a new contributor. Because I thought, okay, my first contribution experience wasn't that great. It'd be great if, these people who have never opened a PR to CPython before can get a response within 48 hours. Whether that's telling them to sign the contributor license agreement or formatting fixes or pinging the relevant core dev or whatever. So that was kind of how I dove into that.
All this terminology that you're using, PRs and stuff. No, this is great. What I was going to say is this is new to Python, right? It wasn't that long ago that Python was on Mercurial, or before then Subversion. It's it's coming over to GitHub is kind of a big deal, and I feel like it's really opened the door for more people to be willing to contribute. What do you think?
Oh, it absolutely lowered the barrier to entry for people like me. Like, using the old bugs.python.org was tough at first, but I eventually kind of got used to it just in time for it to be replaced with GitHub issues, which I much prefer. But I have a hard time seeing myself, emailing patches around, or, I have a lot of respect for people where that was the development flow, a number of years ago. Yeah.
Yeah. Cool.
Yeah. So I became a core developer in 2020. And I guess it was about exactly a year ago, almost exactly a year ago, I joined the Python performance team here at Microsoft.
Were you at Microsoft before then?
No, I was not. I worked for a company called Research Affiliates in Newport Beach. And I think you actually had my old manager, Chris Ariza, on the show.
I have had Chris on the show. Yes. That's fantastic.
Yeah.
Wow. Small world, huh?
Yep. Small Python world.
Yeah, small Python world. Just a couple million of us. No, that's great. So this brings us to our main topic, and let's start at the kind of the top, I guess. There's the faster Python team, I guess. I don't know. How do you all refer to yourself?
We refer to ourselves as the faster CPython team. I think internally our distribution list is the CPython performance engineering team, which sounds a little gnarlier, but it's less. it's a lot wordier.
That's a cool title to have on a resume, isn't it?
Yeah, I think I'll use that one.
There you go. There's been a ton of progress, and some of this work was done in 3.10, but there's this article here that I got pulled up on the screen. It says Python 3.11 performance benchmarks are looking fantastic. That's got to make you feel good, huh?
I mean, they were looking fantastic back in June. It's a small bit more fantastic now. So yeah,
exactly. This article's from June, so this is it's only better from here on, from there, right?
Yep. Yeah. And no, it's really exciting, and like I said, this is a performance jump that, at least since I've been involved in Python, we haven't seen this in a point release. Where we're seeing 25, 30%, sometimes more improvements for pure Python code, rather than kind of the 5, 10, 15% range that might be more typical. And again, I think that's kind of a product of this very conscious effort, whether it's my team or a lot of the people that we interact with. So, for example, Pablo, release manager, steering council member at Bloomberg, has been working a lot on this stuff with us.
Yeah.
Outside contributors, two that come to mind are Dennis Sweeney, Ken Jin. There's definitely been a focus on this, and it's paying off, which is really exciting, like you said.
Yeah, and maybe a little bit more in parallel instead of a cooperative effort, but there's also the Cinder folks over at Meta, Facebook.
That's absolutely a cooperative effort.
Okay.
Even though Cinder isn't necessarily, we're not merging all of Cinder back into CPython. Several of the changes are being upstreamed into CPython. And in fact, just earlier this week on Tuesday, we had, I think, like a 2-hour meeting where the Cinder team walked our team through how their JIT works. So
Nice. Okay.
yeah. So it's, even though, it can be seen as a parallel effort, I think it's very collaborative.
I think also, I, like you, am very much blown away at the step size of the performance improvements. It's just super surprising to me that a 30-year-old language and a 30-year-old runtime can get that much better in that short of a time.
Yeah, and I think, again, I feel like I'm going to keep coming back to this, but having full-time people dedicated to this, having teams of people dedicated to this, I think that's a big part of sort of unlocking this, because some of the things that are required for those big jumps are kind of larger architectural changes that a single volunteer who's doing this on their free time probably wouldn't have been able to do without coordinating with others and without throwing a significant amount of effort at it.
Yeah, I mean, there are people out there, core devs, who have done amazing stuff.
Mm-hmm.
Shout out to Victor Stinner. I feel like a lot of the performance stuff that I've seen in the last couple of years, he is somehow associated with some major change. But the changes that are being undertaken here, they're much more holistic and far-reaching, and it really does take a team, I think, to make it reasonable, right?
Yeah, and what's cool about the 311 effort is it's a combination of kind of both sorts of changes. So we have a bunch of kind of one-off, very targeted changes. Probably 5 or 6 or 10 of those, and then we have 1 or 2 of these kind of larger changes that we can build upon in the future, and they're never really done.
Right.
Which that's exciting, because it means we get to keep making Python faster. Yeah,
it is exciting. I think another area to just highlight real quick before we get into too much detail is, correct me if I'm wrong, but none of this is particularly focused on multi-core parallelism, right?
No. So one member of our team, Eric Snow, he's basically the sub-interpreter guy.
Exactly.
Yeah. He is focusing most of his time on a per interpreter kill and all that sort of stuff. But I mean, all the numbers that you're looking at here and all of our benchmarks, it's all single-threaded, single process. If you're running Python code, it will get faster without you changing your code, which is awesome.
Yeah, it's super awesome. I want to highlight that because if Eric manages to unlock multi-core performance without much contention or trade-offs, or if you've got an 8-core machine and you get 7x performance by using all the cores, like, that would be amazing. But all of this work you're doing applies to everyone, even if they're trying to do that stuff, right? So even if somehow we get this multi-core stuff, the computational multi-core stuff, working super well, the work that you're doing and the team is doing is going to make it faster on every one of those cores, right? So they're kind of multiplicative initiatives, right? So if we could get a big improvements in the parallel stuff, it's only going to just multiply how much better this aspect of it's going to be for people who use that, right?
Yeah, no, absolutely. It's great to be kind of pursuing all these different avenues because they pay off in different time frames, right? Some of these are longer efforts. In Eric's case, the sub-interpreter effort is a very long effort, and I think he's done a great job of sticking with it and seeing it through. And some of these we're seeing in point releases, and so they absolutely build on each other. Like you said, if you can get a 7x increase from sub-interpreters, just to throw out a number, but Python as a whole got 25 or 30% faster, then you're seeing much more than a 7x increase.
Right, absolutely. So very, very exciting times. 2 things before we get into the details of the particular interpreter and stuff.
Yeah.
Tell me a bit about this team. I interviewed Guido and Mark Shannon a while ago. When was that? That was about a year ago, I suppose, about this plan when they were kicking it off. And we didn't have these numbers or anything, but we did talk about what we were doing, and he talked about the team that he's working with there. So said certainly it's just more than the two of us. Tell us about the team.
Yeah, so I think there are 7 people. So there's Guido and Mark, Eric and me, as we mentioned, another core developer, Irit, and then one other engineer, Elle, and a manager for the team who also does some engineering effort as well and is a member of the triage team, Mike Drapu.
Yeah. Nice. Yeah. He worked on Pyoxidizer, right?
Pyodide.
That's right. Pyodide. Yeah, I don't know why.
There's so many pi something or something
molecule
pi.
on the end. Exactly. Pyoxidizer. That's right. That's the foundation for PyScript, actually, which is quite cool.
Pyo 3
okay,
is
the other
cool
question.
Too.
Yeah. The other thing that I want to ask you about is, so we have these numbers and visibility into Python 3.11 that's got a lot of conversations going. People are saying they're looking amazing and fantastic and other nice adjectives. But this is in beta, maybe soon to be RC. I'm not sure what is Python 3.11 status these days.
3.11, we just released our last release candidate, I think this week.
Right.
So this, if basically the idea is the final release candidate and the actual 3.11.0 release should be the exact same thing. So unless we find any serious bugs that merit, fixing before 3.11.1, the release candidate is going to be 3.11. So
awesome.
This is as close to stable as any of the
almost there, right?
get.
Okay.
Yeah.
Cool. So the reason I asked that is a lot of the work you've been doing recently is probably on 3.12, right?
Yes. Yeah. So beta freeze, which is basically when we go from alphas into betas, and there's no more basically new features allowed at that point. That happens every May. And so everything that we've been working on since May goes into 3.12.
Are you excited about the progress you've made?
Yeah. Yeah. Very excited.
It's still coming along well?
Yes. Yeah. And it's nice. We still have a lot of time before the next beta freeze too. So.
All right. Yeah. Awesome. Let's talk really quickly about the faster CPython thing put together by Mark Shannon. Guido called it the Shannon plan. And the idea is, how can we make Python 5 times faster? If we could take Python and make it 5 times faster, that would be a really huge deal. And again, none of that is multi-core. If you could somehow, unlock all the cores and you've got 8, that's 35 or, 40 or something like that. So this is an ambitious plan. It started out with a little bit of work with 3.10. Is that when the adaptive specializing interpreter first appeared, or did it actually wait until 3.11 to show up?
No, I don't believe we don't have it in 3.10.
Yeah, I didn't think so either.
Missing something. Yeah. I think. Yeah. So that's in 3.11. The rest of it looks accurate though.
Yeah. Cool. So. Some stuff. Yeah. So then basically that was stage 1. Stage 2 is 3.11, where there's a bunch of things, including kicking over the interpreter we're going to talk about, the specializing interpreter.
Yep.
But bunch of small changes here. And then stage 3 for 3.12 is JIT. Have you guys done any work on any of the JIT stuff?
Right now, it's not looking like 3.12 will ship with a JIT. We think there are other changes that we can make that don't require a JIT that will still pay off. We're probably planning on at least experimenting with what a JIT would look like. Like I said, we already have gotten kind of a guided tour of Cinder's JIT. And so we're talking kind of high level architecture and prototyping and that sort of thing. But I would be surprised if 3.12 shipped with the JIT. But
sure.
it's a long effort. So starting
research
now
is being done.
Part of that. Yes, actively.
Yeah, cool. All right. Well, this was put together quite a while ago, back in 2020, as here's our plan. And of course, plans are meant to evolve, right? But still, looks like this plan is working out quite well because of the changes in performance that we saw already in 3.11 beta, and pretty fantastic. There are a bunch of changes here about, things like zero overhead exception handling. I believe there was an overhead for entering the try block,
Yeah,
even if
every
there was
time you
no error
went in
previously,
or
right?
out of a try accept block. So even if I did try pass accept pass, there was overhead associated with that.
Right.
Yeah. So basically, we would push a block that says, "Oh, if an exception happens, jump to this location." And now what we do is we realize, oh, we actually have that information ahead of time when we're actually compiling the bytecode. So since the common case is that an exception isn't raised, then we can store that data in a separate table and say, oh, if an exception is raised at this instruction, then jump here, without actually having to do any of that management at runtime. So it's a little more expensive, I believe, if an exception is raised. But in the case where an exception is not raised, I think it is basically as close to truly zero cost as possible.
That's really cool.
Yeah.
I think that's the way it should be. Exceptions, as the word implies, is not the main thing that happens. It's some unusual case that has happened, right? So not always, but often means something has gone wrong. So if something goes wrong, well, you kind of put performance to the side anyway, right?
Yeah. Well, and a lot of the sort of optimizations that you want to see, especially in, for example, JIT code or whatever, exceptions are the sort of thing that mess that up. Where if an exception is raised, okay, get out of the JIT code, go back to the slow land where we know what's going on and have better control of context and everything.
Mm-hmm.
But yeah, no, it's really exciting to see. It's really cool design. And yeah, it was Mark Shannon who did this. It was Mark Shannon who did a lot of this stuff. Yeah.
Yeah, very cool. So there's a bunch of improvements coming along, but what I want to really focus on here is the PEP 659, the specializing adaptive interpreter. And in addition to being on the team, you've created a really cool project, which we're going to talk about as soon as we cover this one, about how you actually visualize this and maybe even change your code to make it faster. Understanding how maybe opportunities might be missed for your code to be specialized or adapted.
Yeah, no, PEP 659, I mean, the concepts are not too difficult, but the implementation is really hairy. So I think it definitely deserves to kind of be gone over in some detail, because it's really cool when you get down to how it actually works and what it's doing to your code.
Is this the biggest reason for performance boosts?
I think it's the most important reason for performance boost. I mean, any performance boost kind of depends on what you're doing, right? Like we did, for example, Pablo and Mark worked together on making Python to Python calls way faster and way more efficient. So if you're doing lots of recursive stuff, that's going to be the game changer for you.
Okay.
We did all sorts of these.
You spend all your time writing loops that just do try, accept.
Yeah.
That one's better.
Yeah, if you've got try accept and tight loops, or if you do lots of regular expressions, then our improvements in that area will probably matter more than this. But this is cool because we can build upon it to kind of unlock additional performance improvements in the future, and we can kind of get into that once we have a better idea of how exactly it works.
Yeah, sure. When I look at PEPs, usually it'll say what its status is and what version of Python it applies to. And I see this PEP, it doesn't say which version it applies to, and its status is draft. What's the story here with that?
Yeah, so I'm actually not sure what the story is behind the PEP itself. I think it's a good informational document that explains, the changes that we did get into Python 3.11. But I don't think the PEP was ever formally accepted. As you can see, it's just an informational PEP. So it's kind of more the design of what exactly we're doing and how we plan to do it.
Right, because it's not really talking about the implementation so much as like, here's the roadmap and here's what we plan to do and stuff, right? But
yeah, there's a lot of kind of
ideas.
Yeah, there's a lot of prose in there that says, here's how we might do it, but we're no promises. We could change this literally anytime, and we have. Yeah. The design has changed fairly significantly since this PEP was first published, but we've updated the PEP so it can remain accurate.
Yeah, cool. Okay, so the background is when we're running code it's not compiled and it's not static types, right? It's because it's Python, it's dynamic, and the types could change. They could change because it just uses duck typing, and we might just happen to pass different things over. I mean, do have type hints, but as the word there is, it implies as a hint, not a requirement, like
Yep.
C++ or C# or something. So you have to have the C Python runtime be as general as possible for many of its operations, right?
Yeah, absolutely. And beyond just types, things like I could create a global variable at any time. I could delete a global variable at any time.
Mhm.
I could add or remove arbitrary attributes from objects. All these sort of very Pythonic things about Python or unPythonic, depending on how you're looking at it.
Yeah.
These are all sort of things that would never fly in compiled languages.
Yeah, and they mean you can't be overly specific about how you work with operations. So, for example, if you say, I want to work with, like, call this function and pass it the value of X. Well, where did X come from? Is X a built-in? Is it a global variable? Is it at the module level? Is it a parameter? Is it a local variable? All these things have to be discovered at runtime, right?
For the most part, yeah.
Yeah, for the most part. Yeah, so part of this adapting interpreter is it will run the code and it says, look, every single time they said load this variable called X, it came out of the built-ins, not out of a module. And so we're going to replace that code, specialize it, or quicken it. I've heard of quickening, so I'll have to work on the nomenclature a little bit.
We can clear up the terms in a bit. Yeah.
Yeah. But you're going to take this code and you're going to replace it, and don't say just load an attribute or load a value from somewhere and go look in all the places. You're like, no, go look in the built-ins and just get it from there. And that skips a lot of steps, right?
Yep. Yeah.
Or maybe I'm doing math here, and every single time it's been an integer. So let's just do integer math and not arbitrary addition operator.
Yep, exactly. With the huge asterisk that if it does become a global variable, or if it does start throwing floats at your addition operation, that we don't segfault or even produce an incorrect result.
Right, because you could say use X. But before that, you might say, if some value is true, X equals this thing. And then it goes from being a built-in to a local variable or some weird thing like that, right? And if it overly specialized and couldn't fall back, well, bad things happen, right?
Yeah, it would be surprising if you were getting the len function from the built-ins over and over and over, and then you, for some reason, defined len as a global. Python, the language specification says it's going to start loading the global now, regardless of where it may have lived before.
Right.
And that's the same for like attribute accesses. If you used to be getting an attribute off the class and then you shadow it on the instance, you need to start getting it from the instance now. You can't keep getting it from the class. That's incorrect. Yeah.
Right. And this is one of those problems that arises from this being a static dynamic language that can be changed as the code runs. Because if this was compiled, wherever those things came from and what they were, they can't change. Their type was set, their location was set. And so then the compiler can say, well, it's better if we inline this, or it's better if we do this machine operation that works on integers better, or some special thing like that, right? It doesn't have to worry about it falling back. And I feel like that ability to adapt and change and just be super dynamic is what's kind of held it back a lot, right?
Yep. And I like that word they used, adapt, because that's kind of a big part of how the new interpreter works. You can change your code and the interpreter adapts with you. If X starts being an attribute on the instance rather than from the class, well, soon the interpreter will learn that sometime later after running your program, and start doing the fast path for instance access rather than class access.
Right. Okay. Well, let's start there.
Okay.
How does it know? Right. It doesn't compile, so it has to figure this stuff out. Right. I run my code. why does it know that I can now treat these things X and Y as integers versus strings?
Yeah. So stepping back a little bit, like how does this new interpreter work? So the big change, kind of the headline is that the bytecode instructions can change themselves while they're running. So something that used to be a generic add operation can become something that is specialized, which is it's a specialized instruction is the terminology we use for adding two integers or adding two floats. And so this happens sort of in a couple different phases. After you've run your code for some amount of time, basically after we've determined it's worth optimizing, because optimization isn't free, so something's only run once. There's, if it's module level code or a class body, there's no reason to optimize that at all for like later runs. Yeah. And so, we have heuristics for, okay, this code is warm. And that's, a term that you hear in JITs often, because JITs have even higher overhead for specializing. And so basically, after we've determined that a block of code is warm, we quicken it, which is that term that you used earlier. And this basically means walking over the bytecode instructions and replacing many of them with what we call adaptive variants. And you can see an example in the PEP, but to kind of walk through that example, if you have an attribute load, once the code is quickened after we've determined it's warm, we walk over all the instructions, and all of the load attribute bytecode instructions become load adder adaptive. And what those adaptive instructions do is when we hit them, when we're actually doing the attribute load, in addition to actually loading the attribute, they will kind of do some fact finding. They'll gather some information, say, okay, I loaded the attribute. Did it come from the class? Did it come from the instance? Did it come from a slot? Did it come from a dict? Did it come from a module? There's a bunch of different possibilities. So using that information, the adaptive instruction can turn itself into one of the specialized instructions. So the example you have here on the screen, it can either be load adder instance value or module or slot. And what the specialized instructions do is really cool. Basically, they start with a couple of checks just to make sure that the assumptions are holding true. So for load adder instance value, we check and make sure that, for example, the class of the object is as we expect. That our attribute isn't shadowed by a descriptor or something weird like that, or that we're not now getting it off of a class object or whatever. And then it has a very optimized form of getting the actual attribute. There's a lot of expensive work that you can skip if you know that you have an attribute that is coming directly off of the instance itself.
Right. Yeah. Or another one is load adder slot. And slots are really interesting for Python performance, and they kind of capture more than a lot of the stuff. The difference of the possible and the common. And by that, I mean, it's possible that every time you access a field off of a class, that it was dynamically added and it came from somewhere else and it's totally new and it could be any type. What's more likely, though, is it's, the customer always has a name and the name is always a string, right? And with slots, you can sort of say, I don't want this particular class to be dynamic. And because of that, you can say, well, it doesn't need to have a dictionary that can evolve dynamically, which improves the access speed and the storage and all of that. And here you all are pointing out that, well, we could actually have a special opcode that knows whenever I access X is a slot thing, skip all the other checks you might have to do before you get there.
Well, yeah, and even accessing the slot is going to be faster. So I'm not 100% brushed up on how load adder slot works, but I mean, the slots are implemented using descriptors. So to get the slot from your class, or from your instance, you still need to go to the class, look up the attribute in the class dict, find the descriptor, verify it's a descriptor, call the descriptor
into that list.
Exactly. We can do it even faster than that. So even if you do have slots, this this happens really fast without even any dictionary lookups, I believe. We say, has the class changed? No. Okay, cool. We'll get to this later, but we remember what offset the slot was at last time, and we just reach directly into the object and grab it. There's no dictionary lookups. We're not calling any descriptors or doing anything like that. It's about as close to, a compiled language as a dynamic language could be. Just verify class hasn't changed. Okay, reach in. I remember where it was.
Very cool. And it's all work. I try to kind of line this up saying the possible and the common. Most likely your code is not changing. And when it's well written, it's probably using the same type. It's not like, well, sometimes it's a string and sometimes like that is the quote 7 and sometimes it's the actual integer 7. Like it should probably always be 1. You just don't express that in code unless you're using type hints, right? And they're not enforced.
Yeah. And getting back to the adaptive nature and making sure that we are correct, if we had something that was a slotted instance coming through a bunch of times and then suddenly you throw a module in or something with an instance dictionary or something else, or maybe the attribute doesn't exist or it's a different type. Those quick checks that I mentioned that happen before we actually do the fast implementation of loading a slot, if any of those checks fail, then we basically fall back on the generic implementation. We say, right. our assumptions don't hold, go back. And if that happens enough times, then we go back to the adaptive form and the whole cycle repeats itself. So if I'm throwing a bunch of integers into an add instruction, and then later I stop and I start throwing a bunch of strings into an add instruction, we'll do the generic version of add for a little bit while we're kind of switching over, but then the interpreter will kind of get the hint and start specializing for string addition later. And it's really cool to see that happen in practice.
Right. So we being Python developers that write code that just executes without thinking too very much about what that means, we should not have to worry or maybe even know that this is happening, right? If everything goes as it's supposed to, it should be completely transparent to us.
Yes. The only way that you should know that anything is different about 3.11 is your CPU cycles, the cloud hosting bill at the end of the month. You should be able to upgrade, and if behavior changes, that's a bug. Tell us about that.
Yeah, for sure. Well, going from this adaptive version, the adaptive instance sounds slightly more expensive than just the old school load adder, for example, because it has to keep track and it does a little bit of inspecting to see what's going on. But then the new ones, once it gets adapted and quickened, it should be much faster. Is there a chance that it gets into some like weird loop where just about the time the adaptive one has decided to specialize it hits a case where it falls back and it ends up being slower rather than faster before?
Well, the worst case scenario would be, you send the same type through, n number of times, and then right when it's going to try to specialize, you send it through a different time.
Exactly. And whatever. If n is the limit, if it goes through n+1 times and then trips it back. Yeah. So that
would be sort of the worst case scenario, but we have kind of ways of trying to avoid that if at all possible. Okay. So for example, if we fail one of those checks, we don't immediately turn into the adaptive form. We will do it after, that check has failed a certain number of times. And as just a concrete example, that number of times that we have hard coded is a prime number. So it's less likely that you'll fall into these sort of patterns where it's like, I send 3 ints through, then a string, 3 ints, then a string. It'd be hard to, get that worst case behavior without being intentionally malicious.
Sure. And on the long, these also, by the way, we got to keep in mind, these are extremely small steps in our code, right? We might have multiple ones of these happening on a single line of what looks like, there's one line of code. There's 5 or however many instructions, bytecode instructions happening, and some of them may be specialized and some of them not, right?
Yeah, exactly. And so the overall effect definitely smooths out. where sure, you may have a worst case behavior at 1 or 2 or 3 individual bytecode instructions, but your typical function is going to have much more than that. Even a smallish function is going to have 20 or 30 instructions if it's doing anything real.
Yeah. If you care about its performance, it'll be doing a lot there.
Exactly. And so some will specialize successfully, some won't, but in general, your code will get 25-ish% faster.
Is there a way you could know? I mean, is there a way that you might be able to know if it specializes or not? We'll get to that.
Yeah.
But it looks like, if I go and use the dis module, DIS, not
Yes.
for disrespect, but for disassembly.
Disassemble. Yeah.
So you can say, import dis, and then, or maybe from dis, import dis. You can say dis and give it a function or something, and it'll write out the bytecode of what's happening. Does all of this mean that if I do this in 3.11, I might see additional bytecodes than before? Instead of load adder, would I maybe see the load adder instance value? Like, will I actually be able to observe these specializations?
Yeah. So if you pass a keyword argument to your dis utilities, then yes, you will be able to see this.
Okay. But if I don't, for compatibility reasons, like load adder adaptive and load adder instance, those are just going to return as load adder?
Load adder. Exactly.
Okay.
Yeah. So the idea is anyone that's currently consuming the bytecode, they shouldn't have to worry about specializations, because the idea is they're totally transparent, so they should only see what the original bytecode was. But if you want to get at it, then if any of the dis utilities, you can pass in adaptive equals true. And that will show you these adaptive instructions. And again, you only see them if it's actually gets quickened, meaning if you run it, a dozen times or so.
Okay. Yeah. So if I wrote, say, a function, and so often what you're doing if you're playing with dis is like you write the function and then you immediately print out the dis output. Maybe you've never called it, right?
Yeah.
And so that might actually give you a different, even if you said yes to the specialization output, that still might not give you anything interesting.
It won't give you it. Yeah, it'll just give you as if you hadn't passed the keyword argument. Because again, this all happens at runtime. So if the code isn't being run, nothing happens. We don't specialize code that isn't ever run.
What counts as warm? How many times do I got to call it?
The official answer is that's an implementation detail of the interpreter, subject to change at any time. The actual answer is either 8 calls or 8 times through a loop in the function.
Okay.
So if your function has a loop that executes more than 8 times, or if you call it more than 8 times, so just calling your function 8 times should be enough to quicken it and specialize.
Right. Well, maybe that number changes in the future, but just having a sense, is it 10 or is it 10,000? You know what I mean? Like, where's the scale before I see something?
Yeah, if you want to make sure it's quickened, but you don't want to take up too much time, I'd say just run it a couple dozen times. As shorthand, when we're writing tests and stuff, we do like 100 or 1,000.
Mm-hmm. Okay.
Yeah. Because that also gives it time to actually adapt to, the actual data that you're sending through it. Because it's not enough to just quicken it, then you'll just have a bunch of adaptive instructions. They actually have to see something.
Yeah, so now we're paying attention. Like, great. you
and
pay attention too, right?
Yeah, and you'll see that too, because if you have any sort of logic flow inside of your function, when you're looking at the bytecode, any paths that are hit will be specialized, but any paths that aren't obviously won't, because we don't specialize dead code.
So it has a bit of a code coverage aspect feel, right?
You could think about it
if you look at it, you might see part of your code and it's unmodified because whatever you're doing to it didn't hit this else case ever. So
yeah, well, and that's what's really exciting about this too, is if you run your code a bunch of times and then you call dis on it, you see a lot of information that would potentially be useful if you were, for example, JIT compiling that function. You see at every addition site if you're adding floats or ints. You see at every attribute load site whether it's a slot or not. You see where the dead code is. You see where the hot code is. All that stuff is sort of getting back to what I said, how this sort of enables us to build upon it in the future. Not only can we add more specializations or specialize more opcodes or do that more efficiently, we can also use that information to kind of infer additional properties about the code that are useful for other faster kind of lowered representations of the code.
Okay. Yeah, I can certainly see how that might inform some kind of JIT engine in the future.
Yeah.
Out in the audience, I don't know how much Julia you know, but there's a
None.
question that says this sounds similar to Julia. I have no idea whether it does or not. But
There is a good chance it could be similar to Julia. I'm not sure, but now I'm going to look it
yeah,
up because I'm curious.
now you got to know.
Yeah. Maybe we can steal something from them. Who knows?
Yeah, exactly. Like, oh, they did do that one thing here. So I think the PEP is interesting. The PEP 659, people can check that out. But like you said, it's informational, so it's not really the implementation exactly.
Yeah.
So let's talk a bit about your project that you did in addition to just being on the team. It's a personal project that you did that basically takes all of these ideas we've been talking about and says, well, two things. One, can I take code and look at that and get that answer? Again, kind of back to my code coverage example, like coloring code lines to mean stuff. And then what's interesting about this, and we'll talk through this example that you put up, is there's actionable stuff you could do to make your code faster if you were in a super tight loop section. Like I feel like applying this visualization could help you allow Python to specialize more rather than less.
Yeah, I mean, in general, this tool is really useful for us as maintainers of the specialization stuff, because we get to see, where we're failing to specialize. Because ideally, if we've done our job well, you should get faster Python without changing your code at all. So first and foremost, this is a tool for us in our work so that we can see, okay, what can we still work on here? But that is sort of a cool, knock-on effect, is that if you do run on your code, you also know where it's not specializing. And if you know
Right.
enough about how specialization works, you may be able to fix that. But I would say a word of caution against, like getting too in the weeds and trying to get every single bytecode to do what you want, because there are much better ways of making your code faster, I think.
Yeah, absolutely. Well, but there are places where you're like, these two functions, I know we got 20,000 lines of Python, but these two,
Yeah.
which are like 20 lines, they are so important and they happen so frequently. Anything you can do to make them faster matters. People rewrite that kind of stuff in Rust or in Python. Before you go that far, maybe adding a .0 on the end of a number is all it takes. Something like that, right? That's kind of what I'm getting at. Not to go crazy or try to think you should mess with the whole program, but there are these times where like 5 lines matter a lot.
Yeah, sure.
Okay, well, tell us about your project specialist.
Yeah, so one really cool thing that our specializing adaptive interpreter does is we've worked really hard to basically make it easy for us to get information about how well specializations are working. So you can actually compile Python. It'll run a lot slower, but you can compile Python with this option with PyStats. And that basically dumps all of the specialization stats.
And you actually pointed out that you can, in the faster CPython ideas section, it like lists out like a
yeah, so there's tons of counters. So you can see that when we run our benchmarks, load adder instance value is run 2 billion times, almost 3 billion times, and it misses its assumptions 1% of those. And yeah, and so there's tons of these counters that you can dump, and that's really cool because we can run our performance benchmarks and see how those numbers have changed. And even cooler than that, it allows us kind of separately to for example, there's been at least one case where we've worked with a large company that has a big private internal app, and they can run it using Python 3.11, and we can get these stats without actually looking at the source code, which is really cool.
And so we want to help you be faster, and we're working on the runtime, but we don't want.
But you don't want to show us your code, and so we're not going to look at it.
You might not want to see it, yeah.
And so those stats are really useful for kind of knowing, okay, 90% of my attribute access were able to be specialized. What about the remaining 10%? Where are they? Well, and then an additional question, like, why couldn't they be specialized? And that's something that's a lot easier to tell when you're looking at the code. And so this tool was basically that my original intention for writing it is, once we get beyond, seeing the stats for a benchmark, can we run something on it that makes it easy to tell at a glance where we're failing and how?
Right. It's like saying
and so
you have
that's what this is.
96% code coverage versus these two lines are the ones that are not getting covered.
Exactly. You get a lot more information from actually getting those line numbers than from the 97% or
Yeah.
whatever. Yeah. And so basically the way it works, we already talked about how in the DIS module, you can see which instructions are adaptive or specialized. And all that this tool does is it visualizes it for you. So literally the implementation of this tool is just a for loop over DIS, where we just kind of categorize the different instructions and then map those to colors and all sorts of crazy nonsense.
Yeah. And for people listening, imagine some code, and here you've got a for loop with a tuple decomposition. So you got for I comma t and enumerative text that you go do some stuff, and it has the I and the t turned green, but then some dictionary access turned yellow, and that it talks about, is it not at all specialized? Is it did it try but fail to get specialized, and things like that, right?
Yep. Yeah. So green indicates successful specializations. Red are those adaptive instructions that are slightly slower and represent missed specializations. And yellow and orange are kind of a gradient, because as we talked about, one line of Python code can easily be 10 or 20 byte code instructions. So,
right.
It's kind of a way of compressing that information into a visually pleasing form. And one thing I want to point out about this too is, you'll notice it's actually, you see characters within a line. And this is something that's really cool, because this is piggybacking on a feature that's completely unrelated to specialization. Originally, when I was writing this, it highlighted each line. So you can see this line was kind of green or this line was kind of yellow. But then I remembered, maybe you're familiar, in Python 3.11, we have really, really informative tracebacks where it'll actually underline the part of the code that has a syntax error or that has an exception that was raised or something.
Right.
Yeah, and so that's the PEP that's linked first in the description there. It's called fine-grained fine-grained locations in tracebacks. Yeah, and so what that means is that previously we just had line number information in the bytecode, but now we have line number and end line number and start column and end column information, which means that due to this completely unrelated feature, we can now also map it directly to which characters in a source file correspond to individual bytecode instructions.
That's super cool. Yeah. So for example, here we've got a string, and you're accessing it by element, by passing an index, and you were able to highlight the square brackets as a separate classification on that array indexing or that string indexing.
Exactly. So it wouldn't have been as helpful to just see that line was kind of yellow orangish. We see that the fast variable store was really, really quick. We see that the modulo operation and the indexing of string by int wasn't that fast. We weren't able to specialize it, but we were able to specialize the key, the lookup of the name key, I, and len. Weren't able to specialize the function call of len on key. So that sort of information, that granularity, is really, really cool.
Yeah, it is super cool. And I think a good way to go through this, you got some more background that you write about here, but we've already talked a lot about specializing.
Yeah, this is just summarizing the PEP.
Yeah, exactly. Yeah. People can check it out there if they want the too long didn't read version. But you've got this really nice example of what may be in the first few weeks of some kind of Python programming class, write a program that converts Fahrenheit to Celsius and Celsius to Fahrenheit, and then just test that round tripping numbers gives you basically the same answer back within floating point variations, right?
Yeah, I really like this example because it as we'll show, it's kind of presented through the lens of performance optimization, but it also does a good job of showing you kind of how the interpreter works and how those little tweaks kind of cascade.
Absolutely. And it highlights certain things you can take advantage of that, if you just slightly change the order, it actually has a different runtime behavior, which we don't often think about in Python. If we were doing C++, we would maybe debate, do you dereference that pointer first, or can you do it in the loop? Right.
Yeah.
But not so much here. So let's go through. I mean, I guess just to remind people, Fahrenheit to Celsius, you would say x equals f minus 32, and then you multiply the result once you've shifted the 0 by 5 divided by 9, and the reverse is you multiply the Celsius by 9 divided by 5, and then you add the 32 to shift the 0 again. And basically that's all there is to it. And then you go through and say, well, let's run the specialist on it to get its output, and maybe talk about this first variation that we get here.
Yeah. So as we were talking about, the red indicates these adaptive instructions and the green indicates the specialized instructions. So we can see here that some things were specialized very well. For instance, look at assert round trip. That's bright green. Because it's in that hot loop, we got enough information about it to say, okay, assert round trip is being loaded from the global namespace, and it's a Python function, so we can do that cool Python to Python call optimization. And that's basically as fast as any function call in Python is going to be. But some things aren't specialized. So the things that jump out, the things that we may want to actually, take a closer look at would be the math, which is, yellow and red. So for instance, the loads of the local variable f in that first function and the load of the constant 32, those are yellow because the math that they're involved in, the subtraction operation, wasn't specialized, but the individual loads of those instructions were specialized.
I see. So half yes, half no for what they were involved in.
Yeah, red, green plus red equals yellow. So that subtraction wasn't specialized, and the reason is in 311, just based on heuristics that we gathered, we determined it was worth it, at least for the time being, to optimize int plus int and float plus float, but not int plus float or float plus int. And so what we're doing here is we're subtracting, a float and an int. And so, we're able to see that that isn't specializable. But if we were to somehow change that so that it was 2 floats or 2 ints, then it would be specializable.
Right, because when I look at it, it looks like it absolutely should have been specialized. I have a float minus an int. The int is even a constant. Like well, this is standard math, and it's always a float, and it's always an int, and it's always subtraction. Right? It seems like that should the math should be obvious and fast. But because, as you pointed out, there's this peculiarity or maybe an implementation detail for the moment.
Absolutely an implementation detail.
Yeah. So if it's an int and a float, well, right now that problem is not solved. Maybe it will be in the future, right? It seems like pretty low-hanging fruit, but
specializations aren't
right.
Yeah, specializations aren't free. So for instance, like when we're running those adaptive instructions, we need to check for all of the different possible specializations. So every time we add a new specialization, that has some cost. And basically we determined, at least for the time being, like I said, that we've tried to do int plus float and float plus int. And at least based on the benchmarks that we have and the code that we've seen, it just isn't worth it.
Sure. Okay.
Yeah. And it's something like int plus int is very easy to do quickly. Float plus float is very easy to do quickly. Int plus float, there's some coercion that needs to happen there.
Right.
Anyways,
so it's already
type conversion.
Anyway.
So so it's not something it's something that costs some time to check, but we don't have a significantly faster way of doing it.
Right.
Which
doesn't happen on a register on the CPU or something.
Yeah, exactly. Yeah.
Okay. So then you say, well, look what the problem is. It's float and int where we have f minus 32, which seems, again, completely straightforward. What if they're both floats? Well, what if, it's going to end up a float in the end anyway? How about make it 32.0 instead of 32?
Yep.
And then, bam, that whole line turns green, right?
Yep. Yeah. So now you're basically doing that entire line using fast local variables and like native floating point operations. You're just adding literally two C doubles together, which is really cool.
Yeah, and this is what I was talking about, where you could look at that line and go, oh, well, I just wrote the integer 32, but I'm doing floating point math. It's not like I'm doing integer math. So if you just put, write it as a constant with a 0, .0 on it, that's a pretty low effort change. And here you go. Python can help you more and go faster, right?
Yeah, and that's not a transformation that we can do for you, because if f is an instance of some user class that defines dunder sub, that would be a visible change if it started receiving a float as the right-hand argument instead of an int. So those are things that we can't do while making the language still the same.
Right, but your specialist tool can show you. And again, figure out where your code is slow, and then consider whether don't just like, well, we only got 100,000 lines. Who's assigned to specializing today?
Yeah, and it also requires this is a simpler example, but it does require a somewhat deep knowledge of how the specializations work. Because for things other than binary operations, it's not going to become clear what the fix is. You just see kind of where I hesitate to even call it a problem, but you see where there's the potential for improvement, but not necessarily how to improve it.
Yeah, and then you have another one in here that's, I think, really interesting, because so often when we're talking about math and at least commutative operations, it doesn't matter which order you do them in, like 5 times 7 times 3. If it's the first two and then the result, or you multiply the last two, and unless there's some weird floating point edge case that the IEEE representation goes haywire, it doesn't matter, right? And so, for example, here you've got, to finish off the Fahrenheit to Celsius conversion, it's the x times 5 divided by 9, and that one is busted too for the same reason, right? Because it's a 5.
Yeah, because so this is kind of for two reasons. This line isn't as good as it could be under ideal conditions. So x is a floating point number, 5 is an integer, so we have the same problem. We specialize multiplication for int and float, but not for int and float. And the division is even a different problem. We don't try to specialize division at all, just for the reason that it's kind of problematic, because the right-hand side could be a 0, and then you have to check for that, and there's all sorts of kind of things that you need to check for that make it not as much of a payoff. So, if we have both an operation that we can specialize, but it isn't being specialized, and then another one that we're not even trying to specialize at all.
Right.
Yeah.
But then back to the commutative thing, you're like, well, what if we did the division, right? What if we did the division like parenthesis 5 divided by 9, and then that x times that, right?
Yep. And so wading through more of these implementation details, Python's compiler, we have a bytecode compiler. It's not compiling to machine code, but it can perform simple optimizations like this. So by changing the order of operations, the bytecode compiler sees, 5 divided by 9, I can do that at compile time once rather than at runtime literally every time through the loop, because that's never going to change. And so by changing that order of
specialization, regardless of specialization, that's better anyway, right? Because that happens when the PYC file is generated, or when the equivalent thing in memory is generated, and then it's just known as a constant, right?
Yeah, and you're doing no division at runtime anymore. So you turn this from 2 operations, one of which is pretty expensive, to just 1 operation. All you're doing is a multiply by a constant now. And so you can see that, once we apply that transformation to our code, everything's all bright green and happy now in there. This is as specialized as it can be.
Right, because in Python 3, 5 divided by 9 is a floating point, right? Doesn't modulo it out or whatever. So then it becomes float times float, which then can be specialized. And that first division part is something that is done at the runtime when it first runs, but only once, which is fantastic, like parse time, basically. Yeah. So this function, or these functions, this code is much better as a result of just understanding.
Yeah, and this transformation isn't something that Python can do for you, because it changes the semantics of the language. Again,
Yeah.
if X is some user object, then it can observe the types that are being passed to it. Or if it's
Right.
like
And
a
if it
array or something,
implements
the D type can get messed
multiply or
up.
whatever, if it implements multiply, it expected to receive the 5. It didn't expect to receive, 1.2715 or whatever the heck that is, right?
Yep.
Yeah, cool. All right. Well, this is a really cool tool. I definitely encourage people, if they're listening, just, come over and there's pictures of code and color. Just scroll quickly through it to see what we're talking about. And I find it super valuable because it highlights with color right on the code that you wrote. It doesn't spit out the bytecode and say, here's the bytecode improvements, but it highlights your code and says the code you wrote is being improved by Python or not being improved by Python here, right? And just understanding that it might not matter and it might matter a lot to you. It depends.
Yeah, and another thing to highlight too that's kind of different about this tool from maybe most tools that you would use is, this isn't static analysis. It's not like MyPy or PyLint where it's running over your code just in its file. You actually need to run your code under this tool for it to be able to do its thing. Because again, all this happens at runtime, so it's only after running the code that specialists can walk over and see where
running the
things were
code
adapted.
Enough, right?
Yes. Yeah. So for example, if I just had this function and I didn't actually call test conversions at the bottom there, at the under name equals main, everything would just be white because nothing actually ran.
Right.
Yeah.
So in this example here, you've got, let's see, 2, 4, 6, 8, 9, surprising that number. You have 9 test values that you're passing in and you're looping over all those values and testing it. So you need to, if you're going to apply this to your code, it's super important that you come up with a scenario of representative data. And for now, n greater than 8. Who knows?
Or it's something that's loopy. It's, it runs loops 8 times or something. Basically, if the same bytecode instructions are being executed a bunch of times, that's how we tell that it's hot, whether that's in a loop or from repeated calls or whatever.
I can see it's pretty easy to forget that. And people might run it and go, it didn't do anything. It did nothing. It's just all white.
Yeah.
Maybe you should
make
add,
sure,
I mean, I'm not trying to issue an audio PR or anything, but maybe it should have some kind of warning. Like if there's 0 color at all, like a warning, like, are you sure you ran it? Because we don't think you did anything.
I actually really like that request. I'm going to do that.
Thanks. Yeah, because you would know, right? Like you'd know if like I've colored nothing, any color whatsoever. Something's up.
Yeah, and I look at it, I'm like, oh, I did something wrong, but someone else is going to be like, Brent did something wrong. So
yes, exactly.
Got to protect my reputation. Yeah.
Well, and just like limit the issues being raised. Like how many times you want to say, did you remember to call it enough times? Yeah. Cool. I definitely think people should check this out if they're interested in seeing how the adaptive specializing adaptive interpreter from Python 3.11 is applied to their code. I guess also other caveat, like really not super handy if you try to do this with 3.10, you got to have 3.11.
It refuses to run under 3.10.
Yeah.
Just because I accidentally made that mistake enough times where I just had the Python environment I had active was 3.10. I'm like, it's not working.
Darn.
Yeah.
It's all
that
white
keyword
again.
argument doesn't exist. Yeah. All that stuff.
Yeah.
So no, you need to be running 3.12, but 3.11 or 3.12. But as you showed earlier, you can download it from python.org. My favorite way of installing Python versions, PyEnv, has had 3.11 dev for a while now. They also have 3.12 dev if you are crazy and you want to try it out. But yeah, you do need a 3.11 to use this.
Fantastic. Well, really great work. I think it's
Thank you.
quite a contribution. It really highlights all the work that's being done in 3.11. So well done.
Thanks.
All right. Now, before you get out of here, I got to ask you the final 2 questions. If you're going to write some Python code, if you're going to work on Specialist, what editor do you use?
I use VS Code.
Okay, right on. And then notable PyPI package, something you came across, you're like, oh, this thing is cool. Maybe not the most popular, but something that you want to give a shout out to.
I thought about this. Can I say 2? Is it only limited
2 is
to
fine. No,
okay,
2's
cool.
good.
So there's 2. I really like creative packages that kind of blur the line between like what is Python and what isn't.
Okay.
So the first one is called PyMetal 3, PyMTL 3, just MTL, yeah,
Got it.
3.
Okay.
This is so cool. It allows you to design hardware using Python. Um, and
Interesting.
you
Okay.
can basically design everything from just a small, set of logic gates to a full chip, and then export it to Verilog and run it on an FPGA. And this is kind of my hardware background coming through. But
Right.
um, yeah, my brother is actually studying at Cal Poly San Luis Obispo right now, and he is on a research team that's designing an entire processor in Python. And so
Wow.
basically the processor itself is designed in Python, and you can test it with Python. So they're testing with Hypothesis, and it's a really cool, creative way of kind of doing this sort of stuff.
Yeah, you don't need any special hardware to make it happen either, right?
Yeah, exactly.
Mhm.
You can just run it on your local machine, and now you've got a RISC-V chip running.
Nice.
Yeah, so the other one is another kind of cool, weird, low-level hardware package. I don't know if it counts as pip installable. It's called PeachPy. I don't know how well maintained it is, but you have to do that thing. Yeah, you have to do that thing where you tell pip to install from like a GitHub link.
Right. Well, you could pip install from a GitHub link. Just
Yeah.
you got to give it a really weird URL instead of just the
Yeah,
name.
yeah.
But yeah. Okay, got it. Sure.
And so this is super cool. It's an x86 64 assembler in Python. So
Okay.
with this, you can basically implement a compiler, or if you feel like it, a just-in-time compiler for basically x86 hardware. So what this allows you to do is in your Python code, it takes care of doing things like allocating hardware registers and labeling jumps and all that sort of stuff. Calling conventions. And so you can specify exactly what assembly instructions you want to execute, assemble them, and then it will package them up in a Python function object, and you can call your assembly code from Python, which I think is so cool.
Wow. And it actually executes as assembly instructions?
Yes. Yeah. So it's segfaults and everything. Yeah.
Yeah, of course. It's the most common thing it does.
Yeah, but I mean, like a simple
That's cool.
example, you can pass in a PyObject pointer and then add, a 8 or 16 or whatever to get the type of it, and then return that, and it will return the type.
Yeah, very cool. So you can see the code example on here for PeachPy. I'll put the link in the show notes. But you do things like create an argument, and then you create a general purpose register, and you load the argument onto the register and whatnot. And you might call the ISA SSE4 operation or whatever. Pretty cool.
Yep. Yeah,
Nice.
so
Those are
cool.
those are really two really good ones. All right, final call to action. People are interested in Specialist and exploring the specializing adaptive interpreter. What do you tell them?
I think the most important thing you can do is download, or if you're feeling like it, build Python 3.11 and try running it for yourself. See if your code gets faster. It probably will. If it doesn't, then Specialist could help show you where it's not. And if that is surprising to you, then you could report it to us. If it's like, oh, my code got slower for some reason, and it looks like this specific pattern is what's causing it. That's something that we care about.
I suspect this interpreter is something that's never done.
Yeah,
right?
there's
you can always
it's Python
more
itself.
Cases. Yeah. I mean, it's clear you could always add more cases. You could make it, decide sooner or easier or more accurately when and how to specialize and add more there's like a lot of stuff you could do, right? As opposed to, now you read CSV files. That part is done.
Yeah, and again, if you're feeling up to it and you've got a huge pure Python app, you can even compile with stats and dump that out and take a peek at it. I think you showed our repository earlier where we have our issue tracker where we kind of just spitball ideas and keep track of work in progress. Yeah, this one. If you go to the issue tracker here.
Sorry, I was wrong. And the ideas one. Yeah. So you've got, it's faster-cpython/ideas on GitHub.
Yeah. So if you go to issues there, that's all our work in progress. And if you have experience optimizing dynamic languages, or if you see a cool research paper or something that you want us to know about, you can open an issue here and this is where things get done.
Yeah, fantastic.
Yeah.
Well, thank you for making Python faster. I think it's really, really important. I mean, I'm always a little bit conflicted because I have some pretty complicated web apps that get a decent amount of traffic, and they've been fine, like really, really fine. Handful of milliseconds response time, and they're doing all sorts of madness with databases and HTML and all kinds of stuff. So on one hand, I don't know if I need Python to be faster, but on the other, people are deciding which language they're going to choose and where they can do their work. And sometimes, either perceived or real reasons, people think Python is not fast enough, right? And so this is important work that will really help some people and will help the community be stronger. So thank you.
Yeah, we love Python programmers.
Right on. Right on. Cool. Well, thank you so much for being here. It's great to chat with you.
Yeah, thanks again for having me.
Yeah, you bet. Bye.